First announcement over on the chat room, if you look at your chats, if you can see that. Over here it says class starts at 1:20. About half of you waited until after 1:20 to try to get in. Please start earlier than 1:20. I'll open the chat room. I'll open the thing up at 10 minutes early, like at 1:10, and let you in. I need to do that to take attendance and find out how my class lists are going. And if you have questions at that time, just turn on your mic and you can start asking me questions. Somebody asked me what I had for breakfast, so let's see. The Zoom links for each session, I'm going to show you on Schoology, this weekly planner that's now planted there. So you can see everything we're doing for that whole week, including homeworks. Waiting room, you're all pretty polite, so I don't need to put all the rules in there. Please look at this. Make a note to yourself, note to self, because I'm sure somebody's going to ask, how do you pay the $20 for this course in lab fees? And that ASB starting October 1st, this is the first chat item here. ASB is gonna, you'll look in there and there'll be a fine, F-I-N-E. Not that you've done something wrong, but it's just a way of keeping track of who pays. There's gonna be a fine for $20 for all of my 80 AP Physics students. So about $12 of that $20 is gonna go to a WebAssign, okay, for that credential that we got, that access code. I bought 85, so many of your friends still want to be in AP Physics. I still have room for 5 more. The other $8 has to do with our contest that we're going to have. How many of you heard about Egg Drop last year? Egg Drop. Half of you, okay. How many of you have done an Egg Drop? Wave your hand. A handful of you. Okay, we're going to do egg drop. You got to protect a raw egg and drop from a certain height. I'm right now negotiating with a helicopter pilot to drop your egg drop devices from way up above the stadium. And the downdraft will kind of scoot them a little bit in the beginning, but then they'll reach terminal velocity and hit the ground, and it's all AstroTurf. So if your egg breaks, then you didn't design it very well. So that's coming up in early November. And then in the spring, how many heard of our bridge contest last year? Bridge contest? Only a few. Okay, you're going to build a bridge, and it's going to try to hold as much mass as possible before it collapses. And we follow the international rules, and we do that after the AP, and that's pretty exciting. I hope we're back in school by then, because this is really fun to watch. So, yeah. So that takes care of that $20. I was just kind of stalling until everybody was here. Okay, any other questions that's in chat already? I'm going to show you the Zoom links. My link wasn't working, had trouble finding the links. I couldn't find the links. School, da, 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 da. Will the fines show up in Skyward? No, it's only going to show up in ASB, where you're going to pay for everything you have to privately pay for, okay? Schoology, okay. So let me go and show you. I'm going to share my screen. I'm going to go to OSD portal. I'm going to go to Schoology. I'm going to go to our course and show you this thing I did. So everybody hang in there. I'm going to share screen. You ready? Here we go. I'm going to go to desktop. Now you can see all the photos I'm working on. I'm going to go over here to OSD portal and let that open up. Can all of you see that I'm on OSD homepage? Wave your hand if that's what you're looking at. Good, thank you. Because I can't tell what you can see from here. So I'm going to go to Schoology, and I'm going to show you a document that I made this morning. And this is how you find it every week. This is good for a whole week. You ready? You don't have to go to Remind. I think Schoology is going to work better for you. Okay, so on this page, it shows that on Thursday morning, you've got a web assignment due, which is 12 questions, 10 points on WebAssign. Okay, you can see that there. But let's go up here to updates. And down here it shows for period 3. Let's see, AP Physics week, starting and finishing. Let's see, week 2 planner. I think it's good for all of you. I think all of these are the same. So this is the PDF, but don't click on the PDF because it's going to download it. Go to View. I did this for the first time this morning, so you have to give me a little slack. All right, I've never done one of these before. So, and it's a document that can be updated. So I have it in my Google Docs, but this is a PDF of it. Okay, so up here you can see that this today we're going to be talking about motion in terms of words, numerical values, and graphically. By the end of these 2 classes, you should be able to tell me speeds and acceleration types. Over here, you should be able to calculate distance, time, speed, and acceleration over here. All right, so that's success criteria. These Zooms for period 3 right down at 120 are the same. I think it's the same link. We have the same link all year long, and there's 51 of them left after today, or 52. So that Zoom should have gotten you here. Chapter 1 is today. We're starting chapter 2 today and actually getting to the middle of it on Thursday. There's a little video I didn't show anybody today, but it's 7 minutes long talking about framework. You should try that. That's a 7-minute thing on AP, College Board AP, My Classroom. And there's one of these for each day of the course. So if you want to watch those, that's kind of an interesting presentation for you. Discuss today conceptual questions, linear motion. You're going to see all this stuff happening. Turning in nothing today. All you had to do was sign up for WebAssign and AP Physics Classroom. So you had to sign up, but that's not there. Let's look at Thursday. Thursday, we're going to continue with our discussions, but we're going to get into accelerations Thursday, which is kind of fun. And then there's a web assignment due 30 minutes before your class. So I'm going to go do that next if there's no questions. Does everybody see where this is? If you have a question now, I can't see chat when I'm sharing screen like this. But if you have a question, you can turn on your audio and ask me.
Mr. O'Leary?
Yes, Paul.
About the WebAssign, after you sign up, it has something about like in 10 days it'll expire or something like that?
Yes, I'm going to go to that next. But all you have to do is put in our class code, and then you can ignore that thing or exit out.
All right. Okay.
Once you have the class code, you're not on a trial anymore. We've paid for you. The school's already paid for all of you, okay? Any other questions, please ask. Okay, so I'm going to try to do this for every week. I'll try to post it on a Sunday night, and that covers us for Mondays and Thursdays. The only thing not on this page right now is going to be your homework that's going to be due the next Monday, which will be chapter 2 stuff. But I don't know how far we're going to get in it today and Thursday, so I haven't made that assignment up yet. Okay, all right, so I'm going to get out of here, back to the portal, and I'm going to go to AP Classroom. And if you want to do this on your own, you can, but just kind of watch me if you want. I'm going to AP Classroom, and this says sign in, and you're going to sign in up here on the right. And if you have an account, I think you can get in this way. Most of you have signed in. So I'm going to submit. And I'm going to go to AP Classroom over here. And there are class codes, joining class codes down here. So why do I want you to be signed up? Well, there's a whole bunch of cool stuff that you can get to. Now that video that I linked for today is right here. This is daily video 1.1 skill, certain skill set. Thursday, I've linked this one. It has to do with velocity and accelerations. But if you look for Unit 1, which is chapters 1 and 2, It goes on, there's about 12 of these guys sitting here. And then at the end, before we take our unit test, there's a little practice if you want, or we can save these before the AP. There's some practice questions down here. Real questions, okay? So, and that covers, if you look on the top, it goes all the way up through our 10 units. All right? So that's kind of neat. All right, so let's go back. Progress dashboard. I'm going to go back to College Board. And I think I can see my dashboard. Let's see what my dashboard looks like. You don't want that. Okay, but eventually I can see how many of you are actually signed in. So, okay, that's AP. Let me go back and get out of this and undo my sharing. Okay, and make sure. Now, if somebody, if you jump out of this session, let me know if somebody's in the waiting room, okay? Because I have on security over here a waiting room. All right, any questions so far? Will the fines show up in Skyward? We're done with that. Okay, it'll show. All right, so I've got a few things I want to do with you. So have a pencil and paper, and I'm going to define a few things first. And I'm going to start here. Okay, I think I'll write it out with you, and then you don't have to be worried about what I'm doing. I'm going to write stuff out for you. Okay. So first things first. You ready? A review of Chapter 1 talks. This is Chapter 1. Talks about 3 concepts. And let me go to Elmo over here. Elmo's my friendly video camera. Sorry. Turn that on, Elmo. Okay, you ready? So there's 3 terms that I'd like you to have some pretty good handle, a good handle on. Okay, the very first thing is called uncertainty. And the chapter presents it, but I want to just kind of reduce that confusion right here. And we're talking about uncertainty of measurement. Measurement. In this case, we're talking about linear. But it could be angular, it could be all kinds of things, uncertainty of measurement. So this is a linear measurement. We did this last class when we measured our can. The uncertainty of measurement is, the standard version is it's plus or minus 1/2 of your smallest division, the tiniest little lines on your measuring instrument, division on your instrument. So this is a measuring instrument. And if I don't write big enough for you, you have to complain, okay? I can zoom in slightly, I guess. Okay, there we go. So if something is illegible or you can't tell what the screen is too bright for us to see. Okay, let me close the window. Is that better? Yep, okay. All right, thank you. So this is uncertainty of measurement. So let's say I measured my can to be 25.7 centimeters. All right, here's our example. And your homework involves significant figures. And how do you carry things along? Well, we can see that there's 3 sig figs, but that 7 told me it's 7/10 of the way between the 5th millimeter line and the 26th millimeter line. I think everybody sees this. I'm going to go rather slow in case somebody misses things. So if I have millimeter, that tells me I have millimeter lines on this thing. So my uncertainty would be plus or minus 0.5 millimeters. Okay. This should be, nope, that's not right. Listen, sorry, go back and make this millimeters. 25.7 millimeters. Then this is half of the smallest division. My fault. If I had a whiteboard, I'd be erasing it a little bit right now. Okay, sorry about that. All right. So if I think we're set there. The other two words I'd like you to know would be precision, and accuracy. Now, your book explains the difference. Most of you know it already. Accuracy says, are you hitting the bullseye when you measure something? Are you hitting the bullseye? That means if I put a 1 kilogram mass on this balance and it's accurate, then I'm going to get 1.000 kilograms. All right. Now, to get that to be perfect, you can usually adjust it a little bit. If you have some standard masses, you can adjust it so it's right on. And there's a little adjustment wheels on most balances anyway. All right. Now, precision says that every time I measure it, do I get about the same answer? That means if I zero it every time and I mass it again, or if I measure the length, of course, the length doesn't really change much, but the balance might, am I getting a clustering of data? So precision is good. That means repeatability. Will it repeat? Or is it all over the place? Okay, which means you can't really trust it. So if you have something that is precise, repeatable, and it's accurate, then you've got a good measuring instrument, and they usually cost more, okay? So simple ones are not necessarily precision or accurate, either one. All right, enough of those. Let's go now to your questions that I asked you to do. And I think I've got them over here on a little PDF, your conceptual questions, all right? So let's see, I'll bring that up here. I think I can do this. Let's go to, no, let me share a screen. Okay, do you know the questions already? Yes or no? Just say yes or no. Do you know the questions already? So I'm just going to go over your answers. Is that all right? We don't need to break you out into little sessions and let you argue about them and all that stuff. We don't need to do that yet. So let me bring up for myself your questions so I know what question I'm answering. So I have these over on the side of my screen. You don't need them, but let's just talk about them. Now you should have 12 questions answered. And I'm going to mention something that you should have in them, and I might add a little bit. So have a pencil handy, if you don't mind. Okay. And it says for question number 1, here, I'll put my answers over here so you can kind of stay ahead of me. How's that sound? Oh, get over there. And you probably can't read this, but that's where I'm going to be using as a reference. Okay, so number 1 said, models are particularly useful in relativity and quantum mechanics where conditions are outside those normally encountered by humans. What is a model? Now, we're not talking about a runway model, all right, or a fashion model here. That's a joke. Sorry, it's in the afternoon. I have to keep you awake. But we're talking about something that's helping us. So I think there's 2 types of models that I would mention here. One is a physical model. In my room, I have a model of a gasoline engine, and it's got all the internal parts to it, and it helps us understand how an engine works, you know, the piston and the rings and the camshaft and all that stuff, and the spark plug. So I call that a physical model, and it helps us understand something that you can't see inside, right? It's got kind of a cutaway view. But it doesn't help us calculate anything. It doesn't help us predict anything. So the other kind of model, to me, is like a theoretical model. So a theoretical model is probably going to be based on a series of equations, and you can input things and find out what should be the result over here. So that's kind of a theoretical or model where you've got a model of how something should work. Well, let's see if the math works out when I do stuff, okay? So 2 types of models. Let's look at number 2. If you have questions, you're gonna have to put it into chat, or you can audibly just interrupt me, okay? How does a model different from a theory? Well, they're two different animals. A model is helping us understand something that's hard to grasp, and we're going to look at one aspect of it with a model. A theory is something that we think we've got, we understand. And a theory is based on a whole bunch of experiments by a whole bunch of people, and they all agree, and the theory incorporates all that understanding into a general rule. Okay? So in the chat room over here, I'd like you to put, type in a couple of some theories that you know about. Type in, just so you have a little list of theories. If I had a list, could you say, these are theories? Okay, type in a few, and then we're sharing that with the class. Go ahead. Type in, oh, there you go. Thank you for typing. Boy, now you're into it. Look at this. Theory of Newton's, actually. Theory of gravity, relativity. That's true. That's from Einstein. We've got theory of evolution. That's not, yeah, that whole theory is evolving, actually. Okay. What else down here? Do I have any new ones? String theory. Yeah, there you go. Any new ones? Yeah, kinetic theory of gases. Good. Thank you, Bahar. And paradoxes count. No, not really. Well, I guess they could, as long as they both meet the criteria for taking into account all things. So let's go on. For me, what determines where are we at? Number 3. If two different theories describe an experimental observations equally well, can one be said to be more valid than the other, assuming accepted rules of logic? For number 3, I would say they're both equally possible right now. If they both can explain everything that's been brought forward, and you can't discount one, then they're equally valid until more things can be done. Okay. Number 4, validity of a theory. A good theory explains everything that relates to that phenomena. Okay. The validity. You haven't said, well, this works, but not for that. You know. So, yeah. So, good theory is validated by being able to explain everything in that direction. Number 5, certain criteria must be satisfied. There are 3 criteria. No. Criteria must be satisfied if measurement is to be believed. Will the criteria necessarily be strict? Certain criteria. You can't ignore data. You can't ignore some results if you're going to believe it. If you're tossing out things at random, then if you get an unexpected result, we call those outliers. You're probably going to say, "Oh man, I don't know about this one," but it might still be your best data. So you got to take into account all data. Number 6, can validity of a model be limited? Or must it be universally valid? Models can be limited. They can be limited to one type of aspect of something. Okay, like I mentioned, the motor. That's what's it look like when it's running? It doesn't tell you temperatures or pressures or stuff like that. To be a theory or a law, theories and laws absolutely take into account everything. Okay. They take into account all phenomena, and they wrap it up into something that covers them. So I want you to, over here on the side, type in 3 or 4 laws. What are some things that you've heard of that are laws? You've taken a lot of science, so you should have a lot of laws here. Laws of motion. Yeah, Newton came up with 3 laws of motion. Law of universal gravitation, that's true. That's from Newton. Law of conservation of energy, conservation of mass. three or four laws of thermodynamics. Yeah, conservation of energy. Actually, conservation of energy is now, we've adjusted the law to be conservation of energy mass. So if you have that written down as an example, it'd be conservation of energy mass. Because of Einstein, E equal mc squared, mass can be converted to energy, energy can be converted to mass, okay? So thank you for all your laws. That was question number 6, was it? Yeah, let's go to 7. Classical physics. Classical physics is, we're talking about Newton primarily, a little bit of Galileo, but a lot of Newton. Classical physics is a good approximation to modern physics under certain circumstances. What are they? So on the side, let's see, there's three things that would qualify us to be able to use Newton's laws. Classical physics. A non-microscopic, yeah, if it's smaller than a microscope can see it, then you're talking quantum stuff. All right, well, that's one. Come on, let's get 2 more. Under 1% of the speed of light, thank you very much. That's true, that's pretty slow compared to how some things move. And weak gravitational. Now, weak gravitational means like Earth's gravity. You and I are sitting in a 1G force field right now, and that's considered pretty darn weak compared to near a black hole. So black holes, these rules don't follow. And subatomically, those rules don't follow. And what was our third one? If you're going really fast, these rules don't follow. You have to have different rules, and that's called relativity, special and general relativity. Okay, thank you guys. So number 8 is exactly the flip of number 7. So if you are going faster than 1% the speed of light, if you're in the subatomic world, and if you're in a strong gravitational field, then you go to quantum mechanics, which is that new form 20th century, 21st century physics. Number 9, can a classical physics describe a satellite moving at 7,500, that's 7.5 kilometers per second. That's pretty darn fast. So over here on the side, I want you to do 2 quick calculations. Let's see who gets it first. What is the speed of light? Type it in. See who gets it first. Who's my hot shots here? Look at all those digits. Oh man. Yeah. So 3 times 10 to the 8th. 3 times 10 to the 8th. These are not quite right. 3 times 10 to the 8th. Yeah, this April, you're close. There you go. Paul, you're there. Nope, Paul's wrong. Come on. So 3 times 10 to the 8th. Don't put all those digits in there. I just want something general. 3 times 10 to the 8th. Now, 3 times 10 to the 8th is 300 million meters in a second. 300 million meters per second, right? There you go. Akia. All right. Now, question number 9 says, are you faster or slower than 1% of that? So now on the chat, somebody get in there. What's 1% of the speed of light? So we can compare them. What's 1%? Yeah, 3 million. There you go. So it's 3 million. So if 300 million is 100%, 1% of that would be 100 times smaller. So that'd be 3 million meters per second is 1% of the speed of light. Now, if we have a satellite over here, how does 7,500 compare to 3 million? It's way, way smaller than 1% of the speed of light, which is where relativistic effects kick in. So what we want to do is say it's so much smaller than 1% of the speed of light, we can use classical physics to talk about the motions of a satellite. All right. Now that means you can describe its trajectory, you can describe its velocity, its accelerations, the forces on it. There's one thing though that you can't do with a fast moving object like that. From relativity, what's true about something that moves really, really fast? What happens from relativity? Type it in if you don't, if you know. What happens if something goes really, really fast? And 7,500 compared to your and my speed, yeah, here you go. It's time dilation. So fast clocks tick slowly, and that's true for satellites too. Now, where do we have to worry about that? We have to worry about that for our GPS system. You know, we have dozens of satellites up there that allow you to triangulate and know where you are and what time it is down here. And they need to have clocks that run properly, but their clocks are they're going to run slow compared to our clocks down here. So we have to know that that change in timing for our GPS satellites. So that's number 9. Okay. If you have any other questions, you can type them in on the side or just break into the audio. Number 10, type in 2 advantages of metric. 2 advantages of metric. As soon as somebody gets it. Easy to convert, that's 1. And let me look for the other one. Used globally, that's the second one I was looking for. So because they're all powers of 10, you just move around the decimal point. If you're in English units, you're going to be talking about dividing by 12 if it's inches to feet. 36 inches is a yard. 1.6 miles, kilometers per mile, all those weird things. It's so much easier to move that around. What countries in the world, if you know, use the English system of pounds and feet and miles other than America? What other countries that you know of use? No, not Europe's metric, as far as I know. Unless you've lived there and know. Koa, have you lived there? Okay. No, everything's metric. Except for, I would say, Australia? Really? Where's Clara? Where's Clara? Is that true?
I'm pretty sure. I mean,
oh, it might be. It might be. Almost the whole world is on the metric system. I would say Canada is dual, okay? And I think England uses a lot of English systems. They don't talk about, but I don't know about their cars. Has anybody here lived in England? I don't know what the speedometers are there. How many of you, wave your hand if you have a driver's license? Wave your hand if you have a driver's license. Well, at least you've been in a car, even if you're not waving a hand. Have you noticed that the newer cars have kilometers per hour and miles per hour on the speedometers? So what's the purpose of a kilometers per hour on your speedometer here? What's the purpose? Type it in if you already know. Why do we have kilometers per hour, whereas America has no kilometers per hour speed limits, speed signs? Kilometers is kilometers per hour in England. Okay. Yeah, Canada. This is for Canada when when we're not being blocked from going up there. So if you tried to drive 100 miles per hour and think that it's 100 kilometers per hour, you're going to get a ticket. All right. So they're way, way different. They're way, way different. Okay. Almost done here. Thank you for hanging in. Accuracy and uncertainty in measurement. Accuracy is how close are you to the target. Uncertainty is how big is the bullseye. So if your uncertainty of measure, if you have a really good instrument, your uncertainty of measurement is small. That means you're pretty sure, even if you're not exactly on the exact target, that you're pretty darn close every time, and you pay for that. Prescriptions, I don't know. Did anybody here, wave your hand if you actually talked to an eye doctor, like you've got a friend or dad or something. You actually did? Whoa, 2 people? Oh, Noah, you did? Come on.
No, I was half listening.
Ah! You just wanted to wave your hand. Cool. What, did you talk to somebody? You did? Whoa. Well, what'd you find out about this diopter thing? No, nobody in my other classes did this. What'd you find out?
From my aunt, who is an optometrist, she said something about how diopters are the unit of measurement of strength of lenses in the glasses, or at least that's what I was told to believe.
That's true. And if you look it up online, like Wikipedia, you find out the power of a lens is 1 over the focal length. So if f gets really, really small, if you have a really curved lens, then it's very powerful. Okay. Did you ask her about the second part? I have no idea about it. It says, which corrections, the sources of uncertainties in prescriptions. Did she say anything about that?
She did not say anything about that. I had to look that one up.
Yeah, because somebody's got to grind these things for you. I mean, I wear glasses all the time, and it looks like a few of you do. Grinding them, you know, who knows how perfect they are, and they don't have to be that perfect, right? Just so they're really close to what we need. Okay, thanks. I'm going to close this out and make it go away. There we go. So any other questions, please put them into chat. We're done with that part. And I'm going to go to some more notes for you. Okay, I'm going to go to some more notes. I'm going to start out with chapter 2 stuff. Chapter 2 stuff, which is going to be, we're going to start with linear motion. And, okay, linear motion. I'm going to take you through we're going to do a mini lab in a few minutes, but I need a few definitions before we get there. Okay, so let's start out. There's 2 types of motion in the universe. Only 2. Everything is either this or that. 2 types of motion. All right, I dare you to tell me what those 2 are. Put it in the chat if you already have an idea. 2 types of motion in the universe. I'm waiting to see who my young Einsteins are out there. Linear and nonlinear. Nope. Nope. Not kinetic. Static and dynamic. Ooh, that's pretty close. Static fits into one of my categories. Dynamic. Yeah, you're close, Ben. That's real close. Okay, good. Thanks. I don't want to give you guys a headache earlier. Okay, so here we go. One is called uniform motion. So if things are in uniform motion, that means that they are not changing speed. I'm going to use a delta for change from now on because I'm lazy. I'm going to use symbols whenever I can. So they're not changing speed or direction. And that's called uniform motion. Now there's 2 forms of uniform motion, and Ben hit one of them. If you're stopped, if something is stopped, it's not changing speed. It's like the book on your tabletop right now. It's not changing speed or direction, okay? Or it's traveling in a straight line. In a straight line with a constant speed. Constant speed. That would be called uniform motion also. I.e., for example, let's say you're in a car going 30 mph, English units, miles per hour, east. On a straight road, no bumps, perfectly flat. You're not going up and down, left or right, no wiggling. That would be called uniform motion, okay? All right. Now, the other one is non-uniform motion. Whew. Surprise, surprise. Non-uniform motion. And that has a special name to it. Somebody type it in over on the side. What's non-uniform motion called? I'm just seeing who knows what, or before I even teach it. Starts with an A. Ends with acceleration. Very good. Acceleration. You guys, come on. Acceleration. Okay? Acceleration. And if you can't see my notes, you have to tell me to kind of adjust it somehow. Acceleration. So an accelerating object is changing speed, up or down, and or direction. It might be going with a constant speed, but it might be turning. So changing direction means turning. So it's either changing speed, turning in a curve, or both. Okay, and then you're accelerating. Now, from your knowledge of science already, you took this when you were in physical science. What causes accelerations? Type it in. Let me see who already knows. What causes things to be in non-uniform motion? Forces, yeah. So if you have an unbalanced force, an unbalanced means you're not countering it. External means you can't do it to yourself. Forces, then you're going to either turn or change speed or both. All right? That's how your car can turn the corner. That's how a satellite can turn the corner. That's how the Earth can go around the sun. You have to have, that causes an acceleration. So, we set? So we're going to do an experiment, and we're going to come up with this idea of what is distance versus displacement. So we're going to do a one-dimensional motion mini lab. One-dimensional motion, okay? And this one-dimensional motion, this will be a mini lab. It's something that takes 5 minutes, but it teaches you something that's pretty cool, all right? And we're going to start out simple today, and then all through the course, I'm going to do these little ones. You'll do some of them, I'll do some of them. I'm going to do this one with you today. Okay, now on the AP, they're emphasizing, why do you do what you do? How are you going to do it? What are you going to do? Why? And what kind of results do you expect? Where's the uncertainties? And how are you going to present that information? So you're going to do a lab. So here's I'm going to tell you the purpose. Purpose of this is to find out how fast my car goes. Okay? Now I brought in my car for you. All right? This is my car. All right? My little red car. And when I turn it on, the wheels go round and round. I don't know if you can tell, but they are going round and round. And if I put it on the table, it goes places, okay? So I'd like to come up with an experiment that I can do in this room with this red car and find out how fast it goes. How fast is the red car? All right, S car go. How far does that S car go? How fast does that S car go? All right, so we need just a little bit of adjustment here when we're going to do a lab. I'd like to, first of all, we need to define speed. If they're saying fast.
Can you move your paper down, please?
Oh, yeah, thanks. Yeah, please tell me anytime I make a mistake. Define fast. Well, fast also equals the word speed. And you have a speedometer on your car, and my little red car does not have a speedometer, okay? It's too small to have one, and it only costs $20, okay? So, and speed is how fast, what's the time rate of change of your distance, okay? And distance is just how far along a track are you, or a line. It could be curved, it could be straight, but distance just means how fast are you going in distance per unit time. Now the standard units for this are going to be meters and seconds. So we have to know what kind of units we're after. Now to do this, we need to set up a good lab, and they're going to ask you to do this about an eighth of the AP exam. They're going to tell you, what do you need to do an experiment to give you this? So we're going to start practicing today. What materials would you like to gather? Okay, what kind of procedure would you do so that we can use those materials to solve for the purpose? And then what kind of data are you going to hope to collect? And how are you going to analyze it and display it so that other people can understand what you did? All right? Okay, ready? Okay, so let's do these things. Let's talk about them real quick. What kind of materials you're going to need? You're going to need three things. You need to have a car. Make sure you write this down. You got to have a car. You got to have some measuring stick, some ruler or tape, and you've got to have
Flat, sir.
a timer. Oh, I don't think it was 3 minutes. Oh, come on. It was probably 2. You guys are fast. Come on. You need some kind of a timer. You also need a ramp. I've got a table. So 4 things. Procedures. We're going to start the car and let it run. And I'm telling you that it doesn't change speed. At least I don't think it does. So we're just going to not do various distances. For procedures, we're just going to let it run a given distance. And how many trials would you like to have? 3. Yeah, I think 3 is sufficient. We could have 5. You certainly don't want to do it just once, because the way I start and stop things, I wouldn't trust that at all. Okay, so we'll drop it 3 times. What kind of data are we going to get? Well, we have a data table. We're going to have 3 runs. That's going to be, now you could do it for the same amount of time, or you could do it for the same amount of distance. I think my table behind me is going to be the same distance each time, and you're going to time it. So I'm going to have 2 or 3 people help me time this thing, and we'll end up with 3 sets of times for the same distance. We okay? Now, I just measured my table, and it's 49.7 inches long. My table is 49.7 inches long. And I'd like to know how many meters that is. Okay, go ahead and do that for me. Now we need to know a couple of things. Oh, there's 1 inch is actually 2.54 centimeters. That's something you'll memorize by the end of the year. It'll just be stuck in your head. And then we need to get from centimeters to meters. So there's 100 centimeters in a meter. And I end up with meters. And I need somebody to type that in for me. Over there, what's the speed, what's the time, the distance in meters that my little red car is going to go? What did you get? 1.24 meters, 1.26. Ooh. Well, we have 3 digits of information in our data. It's 3 and that's 3. So I need 3 in my results. So it looks like 1.2. Oh, is it 4 or 6 out there? People are saying 6. So the 4th digit has to be less than 5 for it to be a 6. 1, 2, 4, 2, 5. Ooh. So that rounds off to 1.26. I'm going to go 1.26. That's 3 sig figs, and that's meters, and that's our distance data. Okay, so all we need now are 3 different times, and these are going to be in seconds. And they're not going to be perfect because I don't know exactly how I start and stop these things. So I'm going to turn this back over to, let's go to video and FaceTime with my car. So here's my little car. Okay, here's my little car. And I'm going to turn this thing on and run it across the table. I need a couple of timers in case somebody screws up. The second one's got it. I need a couple of timers. Where's my timers? There's 1. Who's my second timer? 2. Okay, 2 timers. All right. Whoever gets it typed up first over here for these 3 times, then we'll use your data. Okay. So let's see. I've got a table back here. Move this chair out of the way. I'm going to turn on my car. You can hear it. It's grinding away. Wheels are moving. So when I say start, go, and then I'm going to run to the other side of the table and stop it. Okay, here we go. Ready, set, go. Stop. Ready, set, go. Stop. Ready, set, go. Stop. That's its purpose in life, is to give you those runs. That's its purpose. Okay, what were the 3 times? Who's offering their data first? Who's my data person? One of you 2 guys, give me your data. Oh, you typed it already. 3.10, 3.10, 3.12. Ooh, that's pretty good. And 3.21. Now, we can either come up with 3 sets of speeds, or we can average the time to come up with an average speed. I suggest we do that. Let's call this T average. Subscript is AVE. Somebody type in, do those, and let's come up with an average. .14. Anybody else? Raise your thumb if you think that's the right one. I got a couple of people. Okay, 3.14 seconds. All right. Not too bad. The first 2 were real close. All right. They were at the same angle, actually, over there. So now we've defined this, so we're going to analyze this, and we're going to say that speed equals change in distance over time. And we're going to call this average speed and average time. So our distance is 1.26 meters, being covered in an average time of 3.14 seconds. And now I'm going to get meters per second. Go ahead and do that and use the correct number of sig figs, and we'll write that in as our result. .401. My last class got .400, so we're actually being pretty consistent here, which is amazing to me, given that I dropped it on the table and grabbed it when it came off. 0.401 meters per second. Now that would be a numerical presentation of the speed. But let's say we want to do a visual presentation. We're going to use a graph. So let's graph this information. And if we had more data, it would be a more elaborate graph, of course. Okay, let me go back to Elmo over here. Where's Elmo? Here we go. There's Elmo. Okay, because graphing is a really big part of chapters 1 and chapter 2. So we're going to really talk about this a lot today. Here we go. So if we wanted to present this information graphically, we could say that here's a distance in meters on the vertical, and time in science is going to always be on the horizontal, at least in physics. And we're going to say that we can start with 0 time and 0 distance. You don't have to if you have data that starts somewhere else. And then we're going to have this time, and we're going to have this distance, and we have 1 data point. So we're guessing that it's a straight line from here to here. We're guessing that it's not changing the rate at which it's covering. In fact, on the box, it says uniform motion cart, okay? So we're going to come over here to this time, which we say is 3.14 seconds, almost like pi. And then over here, we have a distance of 1.26 meters. If we had graph paper, of course, we'd do this kind of really cool. Scale everything out. And we'd put a title up here. If we had to turn it in, we'd have a title. Okay. Now we're assuming, though, that from the beginning of timing to the end of timing, that this thing is constantly moving without speeding up and slowing down or turning. Okay, that's what we're saying. Okay, so one interesting thing here is that the slope of this graph, of course, for all you calculus students, what would the slope represent? All you calc people. What would the slope represent? Speed, yes, but is it a derivative or, yeah, it's the first derivative, right, of the distance formula. Okay, so this is the slope's going to equal speed. The slope of a d versus t graph is equal to speed. Okay, easy. So the slope of this graph actually is how tilted is my pen, right? So that tilt tells us the higher the tilt, the higher the speed. The lower the tilt, the lower the speed. And it's also called rise over run from your algebra days, which you may have done in 8th grade when you were just a wee little one. And the rise in this case, we have a delta D and run is delta T. And we have, for the rise, we have distance, right? So that's 1.26 meters. And for the run, 3.14 seconds. So this speed, we're going to call that a V without an arrow above it. V stands for velocity eventually, but we're going to call that speed. If it doesn't have an arrow, it's called speed. It's velocity without knowing direction is called speed. And that's going to be equal to the number we just calculated, 0.401 meters per second. Put a double line down there. So this is a non-accelerating object that's going in the same direction at the constant speed. And we're guessing if we had other distances marked off, we should be able to get them and they would be along that line. Any questions so far? Okay. So now let's go and talk about the difference between distance and displacement. Distance is something that you can do running in circles. Displacement is also where are you from where you started. And one is called a scalar and one is called a vector. Okay, so we're going to get into that kind of difference right now, and they're really different. So let's talk about distance. So distance, we're going to use the little letter D, okay, and that means how far have I traveled? How far have you moved? A long line. Okay, now that line could be curved, could be a track, could be uphill, downhill, round in circles, straight lines, all that kind of stuff. So just if you were walking along a rope, no matter what direction it was going, how many meters have you gone? So the standard units are going to be meters for this. Now it's a scalar because a scalar has quantity only, quantity. No direction. It only has how much is there, okay? So we're going to give some examples now of scalars, i.e., let's put distance, and let's come up with a few more. Type them in, let me see. What else do we know that has no direction involved with it? Time, speed, that's a V with no arrow on it. Can you think of anything else that has no direction to it? Besides your little brother or sister. That's a joke. Can you think of anything else? Okay, how about mass in kilograms? Okay. All right. Now displacement is a vector. Displacement says, how far are you from where you started? Or from a reference point? How far from where you started? Okay. So if I ran around in a circle and I ended up where I started, oh, density. Okay. Somebody wrote density up here. Okay. And that's a row. We did that last class. That's a row. Okay. So if you run around in a circle and you ended up where you started, you have no displacement. You're not displaced from where you started. But if you moved 5 meters to the east, that would be a displacement of 5 meters east. Everybody got it? So an example of distance would be 5 meters. And the displacement, if I move, could be 5 meters east. And you would know exactly where this thing is at the end from where it started. Okay? So let's do 4 scenarios. These are interesting little ideas, and we're going to try these. I know I only have 15 minutes left, but first period never got this far, so you guys are a little quicker than first period. But don't tell them that, or they'll get mad at me. Okay, here we go. I'm going to give you 4 scenarios. I'm going to do 10 meters each time. I'm going to go from A to B, and I'm going to walk 10 meters in 10 seconds. And it's a circle, okay? Now I'm going to walk away up a ramp 5 meters, and then I'm going to turn around and come back 5 meters. This is B, okay? I'm going to go up and turn around. The time to turn around is instantaneous. It's a special person that can do that. Next, I'm going to walk away 10 meters. And then this is A and this is B. And then in the last situation, I'm going to come back from here. I'm going to come 10 meters back. Okay? Now, we should be able to come up with graphs of all 4 situations that have some differences to them. Now, this is going to be a distance time graph on the top.
Could you move the paper down a little bit?
Sorry. Yeah. Thank you. Yeah, you keep telling me. All right. So these are distance time graphs, and these are going to be displacement time graphs. Displacement time graphs, which means direction becomes more important, and it's different. So I'd like to come up with 8 graphs. Hey, let's do these because I'm running out of time. I have 10 minutes to get those last things done. You ready? Now I'm going to stay in the middle. I hope you can see. I'll zoom in slightly. Okay, there we go. Each of these 4 runs, if they were you, covered 10 meters in 10 seconds. So they're all identical. Okay? They all did 10 meters in 10 seconds. The slope is 1 meter per second, is how fast they're traveling. So if you have a speedometer on you, it would say 1 meter per second in all 4 situations because you kept moving, right? We're ignoring the turnaround time here. Okay, so that one's good. The other ones are a little trickier. Well, the third one here, we moved away. And so that's identical. This is 10 meters in 10 seconds again. So this one's the same. It went a positive. Now we have to define positive. So we're going to say positive is to the right and negative is to the left. Okay? So negative displacement. So let's come back to this one. We went away 5 meters, went farther away 5 meters, and then we came back 5 meters to where we started. So this is a 5 meter line. We went away 5 and came back 5, okay? So actually we're back where we started. And this one's the same. So here we're getting farther away and then we come back. So we know the endpoints. We got to come back to where we were. So we're going farther away. It's some kind of a curve. I'm not sure exactly, okay? We went away and we came back. Now here, we came back. So how are we going to do this? We're starting out, we're going to the left. So let's see, we're at a negative, we're going to the left. So we're already displaced. So we're already displaced by what? -10? Is that it? -10? And then we're going to come back to here. I'm not sure about this one.
Doesn't it start positive and go down negative?
Yeah, we're 10 meters away, and then we come back, and then we have a negative slope. So this is -1 meter per second for a slope. That's probably better. Okay, so that's your speed for that. That's the slope of that last graph. Okay, the last thing we want to mention is just a little review, and that is, what if you don't go?
Can you move your thing down?
Do what? Say it louder.
Can you move down, please?
Oh, yeah, sorry. Sorry. All right. I can, all right. So let's say I went 5 meters east. Let's call this east. And 5 meters north. And I'd like to know what my displacement vector is. This is a review for you. Okay. Of course, we have a right triangle. And we know that that displacement vector is going to be equal to have some distance to it and some angle to it, okay, because it's a vector. So this is vector A plus vector B equals the resultant vector. So we're going to do the Pythagorean theorem, A squared plus B squared equals C squared. And since this is pretty easy, this is C is going to be the square root of 50, 5 squared plus 5 squared, so that's 707. You don't need a calculator for that one, okay? So that's the length of it, but what is this angle theta? What is that angle? Well, if it's an isosceles triangle, all of you remember that that has to be what degrees? 45, right? 45 degrees. And later we're going to use SOHCAHTOA if it's not easily remembered. We'll use the 3 trig functions, sine, cosines, and tangents, okay? Now, how do you represent 45 degrees? Well, 45 degrees compared to what? In physics, we call it to the right, or to the east, or to the right. We call it 0 degrees. We're going to go counterclockwise and get to 90, 180, 270. So this 45 degrees is here, okay? Can all of you see that? Just making sure you and I are on the same page, literally, okay? Literally. Okay. Next is just a little note about WebAssign. WebAssign has a special way, you're going to discover this, of presenting big and small answers. Let's do 500. Now, 500 would be 5 times 10 to the second. Oops, no. That's not right. 5.00. The decimal points there, those are all 3 significant. Scientific notation says 5.00 times 10 to the second. Okay? That would be scientific notation. On WebAssign, they're going to say 5.00 E2. That means E means times 10 to the. That's what the E means. Okay, and you probably knew that already before. Okay? And the other thing to mention is that if you're, did I mention your OpenStax book? Use the 2020 version of your OpenStax book. The one I had posted before I saw it was revised was 2019. Okay, so the downloadable PDF and the connection online is 2020. Okay, so wrapping it up, we've done uncertainties. We did what uniform versus accelerated motion means. We've talked about how to set up a simple lab. We've talked about graphing linear motions, not necessarily in a straight line. Right. And we've talked about a little bit of review of vector addition and powers of 10. So your homework basically is to finish those simple 12 questions on WebAssign. Did I show you WebAssign? I did, right? Did I or didn't I? Did I not show you WebAssign? I did, right? Okay, so there's 12 questions worth 10 points. I try to keep everything, homework's about 10 points, so it's no big deal. You get 5 chances at each question, and if you miss it 5 times in a row, you deserve to get a 0 on that question. Okay, before you waste all 5, you can ask somebody, including me, and look into chapter 2 and try to get up to where I am right now, so that I can continue on Thursday. So I'm going to stop you. We have 2 minutes left officially. So I'm going to stop right now, and I'm going to say sayonara again, and until Thursday. And then if you want to stay on the line, you can open your mic. This will be open mic time, and you can ask me questions or tell me jokes or stuff like that, and I'll help you. I'll stay on until everybody's gone. So So are we supposed to read any of chapter 2? Yes, try to read up to where you think we are right now, which is linear motion, graphing linear motion, speed graphs. See if you can get up to there. Okay, you don't have to read the whole thing because you've also got a little mini homework assignment to do. And I will transfer the grades from WebAssign to Schoology. So you won't see them in Schoology, I think, until I transfer them myself. Okay, and you have lots of chances to finish that until Thursday morning. Okay, I'm going to say goodbye, and you can leave. Go ahead and leave. Go ahead and leave. And then if you want to stay on the line, bye. It's been fun. Thank you for being here at the end of the day. Please stay on if you have questions. I'm staying here with you for the next few minutes.
I'm that old bitch you get on, gravitational, root 2 GM over R, it's inescapable, cause I can find velocity, Miss Mills she taught me, gonna get 5 on this exam, that's a guarantee, elastic collisions I've been observing, your momentum don't need conserving, my love for friction is concerning, when you talk physics to me.